Final installment of the uniform circular motion exam style questions. So we're up to question 7, and it says figure 1 shows a parcel on the floor of delivery van that is passing over a humpback bridge on a straight section of road. The radius of curvature of the path of the parcel is r, and the van is travelling at a constant speed v. The mass of the parcel is m. Okay, so we've got going along a straight road and it goes over this bridge, of which is part of a circle of radius r. And then we've got this parcel, it's on the floor of the van. It says draw arrows on figure 2 below to show the forces that act on the parcel as it passes over the highest point on the bridge. Label these forces. Well, we've got the weight of the parcel, and then the normal contact force, the reaction to the ground. I suppose I'll call it R for reaction. And they're the two forces acting. And so that's that one. Then it says write down an equation that relates the contact force R between the parcel and the floor of the van to M, V and R, and the gravitational field strength G. Okay, so if we think about these two forces, now actually when it's going in this circular path, there must be some resultant force acting down. So in this scenario, R will have to be smaller than W, so that there is a resultant force, which is the centripetal force. So W minus R would give us this force acting towards the centre of this circle, and centripetal force so is mv squared over r, always equal to that, and the weight of the box is mg minus r. Okay, and if we want to put that in terms of r, then r would equal, if I add r that way and take away mv squared over r, I've got mg minus mv squared over r. I can pull out the mass if you would like, g minus v squared over r. So use an expression, and what it suggests is that r would be at a maximum when it's not moving. So if there's no speed, this is 0, and then the reaction force is the weight of the object. However, as this increases its speed, this term then increases, taking away from this. So it's removing some force away from the weight. The reaction force goes down. Next question, calculate R if M equals 12 kilograms, R equals 23 and V equals 11 meters per second. Okay, so we had the reaction force was the mass times G minus V squared over R. So if I replace M with 12 kilograms, I multiply that by 9.81 minus 11 squared divided by 23. That comes out at 55 newtons. Okay, so the answer is 55 newtons. Okay, so although the weight's approximately 120 newtons, the reaction force is just 55 newtons. So the force acting towards, the resultant force acting towards the centre of the circle is great enough to cause it to move round at that speed in a circle. B. Explain what would happen to the magnitude of R if the van passed over the bridge at a higher speed. What would be significance of the van speed being greater than 15 meters per second? Support your answer with a calculation. Okay, well we're kind of just talking about what I was saying earlier, in that the faster you go, the larger this term becomes. So then you've got G minus that larger number. So overall this goes down, so the reaction force goes down, and there's going to be a limit to when the centripetal acceleration equals the gravitational acceleration. Okay, so we can do a little calculation. If we said that the reaction between in this case the parcel and the ground, if that became 0, so it actually was lifting off from the floor, so if that was 0, then mg would equal mv squared over r. And then we can cancel the m's and we can rearrange this for v, so multiply it by r and square root it, so the velocity, this is the maximum velocity, so that the reaction force becomes 0, so it lifts off. And if we just put some numbers in, 9.81 times the radius is 23, square root of that, and that comes out as 15.02 meters per second. So in other words, as we're getting closer to 15 meters per second, the reaction force is getting closer to 0, and eventually if you go over 15 meters per second, this is going to kind of launch the box off the ground. Right. Question 8. Figure 1 shows, not to scale, 3 students, each of mass 50 kilograms, standing at different points on the Earth's surface. Student A standing at the North Pole, student B standing at the equator. The radius of the Earth is 6,370 kilometers. The mass of the Earth is 5.98 times 10 to the 24 kilograms. In the question, assume that the Earth is a perfect sphere. Use Newton's gravitational law to calculate the gravitational force exerted by the Earth on the student. Okay, so let's just pull out some numbers here. We've got the mass of the student is 50 kilograms. It's given us the radius of the Earth. I'm going to put that as 6.37 times 10 to the 6 meters. I've converted that to meters. The mass of planet Earth is 5.98 times 10 to the 24 kilograms. And the gravitational constant, 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. So what it's saying is using Newton's gravitational law. Okay. Now you might note that gm over r squared is actually the gravitational field strength. So really, you could also say that the force is mass times gravity. This whole term is g at the surface of the planet at this distance away from the centre, but we'll just plug all those numbers into here. So we've got 6.67 times 10 to the minus 11 multiplied by 5.98 times 10 to the 24 multiplied by 50 divided by 6.37 times 10 to the 6 all squared. And every term's of 3 significant figures, so I'll put minus to the 3 significant figures. That comes out as 491 newtons. Okay, figure 2 shows a closer view. Okay, figure 2 shows a closer view of student A. Draw on figure 2 vector arrows that represent the forces acting on student A. Okay, so weight acts vertically down, and there is a contact force, a reaction between him and the ground, that person and the ground. So that's that. Now it says, show that the linear speed of student B due to the rotation of the Earth is about 4,600 meters per second. Okay, so what we want to work out then, let's see what we've got. So we're trying to suggest that that's the actual speed, and what we can say is when you're moving in a circle, your velocity can be worked out by knowing how far how long it takes to go around, so the time period of rotation, how far you travel, the circumference of that circle. So the time period for the Earth to rotate once is 24 hours. If we times that by 60, we get minutes, and then times by 60, we're going to get into a time in seconds. And R, we know from the previous question, was 6.37 times 10 to the power 6. And now we've got everything to say that the linear velocity, 2 pi r over t, that's going to be 2 times pi times 6.37 times 10 to the 6 divided by 24 times 60 times 60. That comes out as 463 meters per second. Okay, so we've shown that it's about 460 meters per second. Calculate the magnitude of the centripetal force required so that student B moves with the Earth at a rotational speed of 460 meters per second. So centripetal force is mass times centripetal acceleration, and that is 50 kilograms times this velocity squared divided by the radius of the planet, and that will come out at 1.68 newtons. Okay, so what we've worked out is that you've got a person, they've got a weight, they've got a reaction. The result of those two things is the centripetal force acting towards the centre of the Earth. Show on figure 1 an arrow showing the direction of this centripetal force acting on student C. Sorry, I had to get it back. So student C, there it is, acting towards the centre. Okay, so the force acts towards the centre, the centripetal acceleration is towards the centre, and that means that the linear velocity always changes direction around that path so that it's tangential. Final question. Student B stands on a bathroom scale calibrated to measure weight in newtons. If the Earth were not rotating, the weight recorded would be equal to the force calculated in part AI, which, if you remember, the force between the planet and the mass of the person came out as 491 newtons. So what we're suggesting is if that person just stood on the scales, their weight directly down, the scales are actually measuring the reaction to that, and that would be equal to the weight. However, because they're rotating, there has to be a resultant force between these, and that force has to be in the direction towards the centre of the Earth, so the weight is greater than the reaction. So in other words, as you're moving in a circle, the faster you want to move, the greater the centripetal force will have to be, the smaller the reaction between you and the ground. So we can do a calculation to calculate that. Well, we calculated that they would need this to be travelling this fast, so they need this force. So actually, what we've got is the centripetal force already. We know the weight, we can work out the reaction of what it should say on the scales, which would be W minus FC. So that was 491 newtons, because the force between the Earth and the mass is the weight of the object, minus this 1.68 newtons, and that would come out as 489.3 newtons. Okay, so it appears that you are slightly less weight than you actually are when you're rotating in a circle, or as the planet rotates and you rotate with it.